Welcome to the second video in the series on statistics. In the last video, we introduced the idea of statistical inference, and I talked about how we might use statistics to estimate kind of characteristic quantities that describe groups of events, people, or measurements. And I laid some of the groundwork for thinking about statistics, but it was very high level, and it may have seemed maybe a bit intimidating, especially if you aren't familiar with statistics or don't have a strong mathematical background. But we'll see that a lot of what we'll talk about are we're going to be talking about quantities that we're used to calculating already, and we're just going to be thinking through what those quantities mean carefully. So let's start by talking about the mean, or the average of a group of measurements. So, for example, suppose that we know from prior information, perhaps we've conducted a study in the past, that employees with advanced degrees in the US make on average $70,000 per year. If we want to answer the question, do people without advanced degrees earn significantly less than people with advanced degrees, we're going to have to make a new study of the salaries of people without advanced degrees in the USA and figure out if their average salary is significantly less than 70,000. So the first thing we'll do is we'll go out and we'll collect data. And there is a lot of thought out there about how to collect a good sample. We are not going to talk about that in this course. It's outside the scope of our discussion. There are, people who think very hard about this and do research on this, and we're going to simply assume that we've collected a good representative sample, so that we can carry on talking about statistics. So say we've collected a representative unbiased sample of 1,000 employed people without advanced degrees, and we get their salaries, their annual salaries. Well, you know already how to calculate an average. To estimate the mean, we're just going to add up all the salaries from our sample and then divide by the number of salaries there are in our sample. So we add them all up and we divide by 1,000. Now, in mathematical notation, we would represent that this way. And it's okay if you've never seen this combination of symbols before. This big Greek letter sigma, capital sigma, just means sum. It just means we're going to compute a sum. And then we have xk here. X is a salary in our case. And each salary is indexed by the letter k. So we have salary 1, 2, 3, 4, 5, 6, etc., all the way up to 1,000. So k goes from 1 to 1,000. N up here would be 1,000. And then once we compute that sum of all the salaries 1 through 1,000, we divide by 1 over 1,000. Or we divide by 1,000. So pretty straightforward. It's just what you're used to in terms of computing means. X sub 1 plus x sub 2 plus x sub 3 plus ... x sub n. So it's just this, which is what you're used to doing to compute means. And we're going to call the average salary x bar. This is our estimate of the average salary, X bar. I want to distinguish it from the actual, the quote unquote actual average salary, which we call mu. So we'll also be using this symbol, the Greek letter mu, for mean. And when we use mu, we're referring to the so-called true or actual average salary, which is a quantity that we can't know. We can't collect all the salary information. We can't collect everyone's salary. And even if we could, new jobs are being created all the time. Jobs are being eliminated as people get fired. So this quantity is constantly in flux, and it's not really knowable. So I've written here that the actual average salary is theoretical or unknowable. We refer to it using the letter mu. And often we will assume some value for mu. Even though it's unknowable, we will assume it has some value. And that assumed value is what we're going to be testing often. That's the claim that we'll be testing in hypothesis testing. So I just wanted to draw this distinction. X bar is our estimate of the average salary, and that is based on data that we have collected. Mu is a theoretical or assumed actual average salary, which in truth is unknowable. Both of these will have some value in our calculations, but they will often be different values. So let's look at an example in code that's going to simulate this situation of collecting the salaries of 1,000 adults without advanced degrees, and then have a look at the average salary. So I'm not going to go over this code because it's mostly just for plotting. But I will highlight here that I am using SciPy, a module or package that I have briefly mentioned in the past, but we haven't made use of yet. SciPy is related to NumPy, and they're very closely related, in fact. SciPy is most often used for its statistical tools, as well as its computational mathematical tools. For example, for computing numerical derivatives or numerical integrals. So for doing calculus in Python. And here we're going to be using some of its statistical tools. So I am constructing a particular probability distribution called a log normal distribution. And it's okay if you don't know what that is. It's not really important, and I'll be plotting it in a moment. But that we're going to use that probability distribution to randomly generate salary data for us. So I'm just creating this probability distribution for generating my salaries and defining a function that is going to do some plotting for me. And now if I run this cell, I can see a few things. So first of all, this black dotted line, dashed line, is a plot of the probability distribution for the salaries. So we can see the mode is here at about $30,000 a year. That's where this probability distribution peaks, but it has this long tail. And if you were to compute the average salary based on this probability distribution, it would end up at this red line, just above $60,000 a year. The blue bars is a histogram of our sample. So here we have a sample size of just 10. And we ended up with 2 people with about $30,000 a year salaries, someone with a little bit higher than that, someone in the $50,000 a year range, a couple people, 3 people in the $60,000 to $80,000 a year range, someone up here at about $90,000, and then 2 people, and then another person over here at over $160,000 a year. The mean of the histogram, the sample mean, is shown in this green bar. So in principle, this black dashed line and this red line are things that we can't know. They are some underlying process that describes the probability of people having different salaries in the United States. And I just made them up. But if we were trying to model the job market in the United States, these might be things that we assume to be true. We might assume that salaries are distributed as a log normal distribution with a mode around this and a certain spread and all that kind of thing. But it's not something we can ever know. And in fact, it's really just a model of a whole bunch of processes happening in the world that are too complicated to account for explicitly. So we say salaries are sort of random, but they are distributed in this way. The blue bars are the data that we've collected. That histogram is our data. And it's no surprise that our sample mean, the mean from our data, the data being random, is different from the true mean, the mean of the probability distribution from which this random data was generated. So for example, another example is if you take a 6-sided die, and you take 2 of them, and you roll those 2 together, the average value you should get after many dice rolls, is 7. But if you roll those 2 dice 3 times, you'll probably get an average value that's different than 7. And it's only when you roll it many times that those average values start to come in very close correspondence. Reliably, anyway. I could run this cell many more times, and each time we would get a slightly different histogram, and a different position for the green bar here. And that's because each time I run this cell, I'm drawing a different random sample of salaries. So probably your random sample will look different than mine in this video if you're following along in the notebook. So we see that histogram change each time I run this, and I'm collecting different salaries. The black dashed line and the red line stay the same each time. They may look different, but that's only because the scale of the window is changing each time I run this. But if you keep your eye on the red line, you'll always see that it's just slightly to the right of $60,000, and the peak of this black dashed line is always right around $30,000. Again, here it's right by 60, this peak is by 30. The peak is by 30, this line is around 60. The line is near 60, the peak is around 30. So just each time I get a different sample of 10 salaries, leading to a different sample mean and a different histogram. If I increase the size of my sample to say 100, we notice a few things compared to when the sample was 10. First of all, the histogram seems to more closely follow the black dashed line. The histogram now kind of resembles that black dashed curve. And that's because since we're drawing many more samples, there's a lot more of a chance to draw salaries kind of all along this range, and we'll draw them more often from here than from out here. Secondly, if I were to run this many times with a sample size of 100 each time, we would see in general this sample mean tends to be closer to the true mean than when I had a sample size of 10. Now, it's not going to be true every time, but most of the time, the distance between the sample mean and true mean will be smaller when I have a sample size of 100 than when I have a sample size of 10. If we take that out to 200, well, I can, let's see here. If I set this to 200, and I run this again and again, we see almost every time the green and the red line are very close when I have to each other when I have a sample size of 200. And every time the histogram resembles the black dashed line. So this matches our intuition. If we roll our dice many times, our pair of dice many times, eventually we'll see a pattern emerge where we roll 2 or 12 very infrequently, but we roll 7 and 8 and 6 a lot. And on average, if we roll the dice 100 times, it's going to have an average value pretty close to 7 every time. If we only roll it once, who knows what we'll get. If we roll it twice, the average value of those 2 dice rolls may not be very close to 7. So this corresponds with our intuition. And a lot of you have probably heard of the so-called law of large numbers. And that's exactly this effect. We'll be talking about that in more detail soon. In fact, the difference between the sample mean and the true mean is a quantity referred to as the standard error of the mean, which we'll talk about in the next video.